Welcome back. In the last part of this section, we're going to look at two more models. One is Newton's law of cooling, and the other is logistic growth. So for Newton's law of cooling, we're talking about something where we have an object that is hot and has been taken out and left to cool down. And you know from your own personal experience, you have a pot of soup on the stove and you turn the stove off, and the pot of soup starts off being very hot and steaming and boiling and starts to cool off pretty fast, but then stays sort of warm-ish for a while, and it actually takes quite a while for the soup to become cold. So when we're looking at things that are cooling down, notice the kind of curve that we would expect to see, something that looks like an exponential curve. And it's one where, again, it's not going to get infinitely cold. The amount of temperature that we're going to taper off to will be whatever the room temperature is. If you're in a room that is 18 degrees Celsius, for example, then no matter how hot you start with your soup, it will eventually taper off to 18 degrees, the room temperature, that there should be a horizontal asymptote at 18. And that's sort of the model that we've got working with here. You'll notice that for our model for Newton's law of cooling, it's basically our exponential growth and decay formula plus a vertical shift. Here, T with a subscript of S, this is the temperature of our surrounding medium, the air that's surrounding whatever the hot object is that's cooling down. So this would be something where if you were to graph it, you would have a horizontal asymptote at whatever that ambient temperature, that surrounding temperature is. And that as time goes on, you should cool down to whatever that surrounding temperature is. The other things that we have here, this K, again, this is our decay constant that is controlling how fast or how slow our object is cooling. And that A, this is not our initial temperature. A is the difference between our initial temperature and the temperature of the surrounding medium. So A is the difference between the initial temperature and T subscript of S. In other words, T of 0, our initial temperature, is A plus T of S. Or in other words, A is your initial temperature minus your surrounding temperature. You don't need to really remember that because, of course, if you're told what the initial temperature is, then you are told what is the temperature when T is 0. You could just use the equation to solve for what A is. And we're going to see this in the next example that I'm working on here, where I've got a cake that I've taken out of the oven, and when I take it out of the oven, the initial temperature for this cake is 98 degrees Celsius. So the temperature when time is 0 is 98. And I know that I'm placing it on a table in a room where the air temperature is 18 degrees, so the temperature of the surrounding medium is 18. I'm also told that after 20 minutes, the cake has cooled to 78 degrees Celsius. So here, I'm going to decide in advance that I'm going to use time as measured in minutes, just to help things be easier on myself. So I'll say that when time is 20, the temperature is 78. And the question is, you want the final temperature to be 45 degrees Celsius. And the question is, what is that time? So this is what we have. We have a bunch of facts. We know the surrounding temperature, 18 degrees. We know the cake starts at 98 degrees. After 20 minutes, it's at 78 degrees. How long does it take to get to be reasonably warm? 45 degrees Celsius. So starting with our formula, T, temperature at time T, is AE to the KT plus our surrounding temperature being 18. And I'm going to use the first fact, which is that when the time is 0, the temperature is 98. E to the K times 0 would be E to the 0. and e to the 0 is just 1. So, as expected, A is the difference between the initial temperature of 98 and the temperature of the surrounding air, 18. So A is 80. So now we've got a good start. We have T and time T is 80 e to the kt plus 18. Okay, so the next thing that we'll need is to solve and find out what is our constant k. And this is where, so we've used 2 out of the 3 facts. The third fact that we'll need to use is that when time is 20, that the temperature will be 78. So 78 will be 80 e to the k times 20 plus 18. And I just need to solve for k. So first, I'll bring the 18 to the other side. I'm going to isolate that exponential expression, so I've got to divide by 80 next. 60 divided by 80 is the same thing as 60 over 80, which is 3/4. And now I'll rewrite this as a log. Natural log of 3/4 equals 20k, or k is natural log of 3/4 divided by 20. So there we go. We've got our constant here for our model, and now I can go right ahead and rewrite my equation involving that constant. I know that t at time t is 80 e to the k times t, and the k that we just found, that was natural log of 3/4 over 20 times t, and then we had that plus 18. So there we go. We've got our equation for temperature at time t, and what we wanted to know was what was our time that it takes for this temperature to become 45 degrees Celsius. So now we want our temperature to be 45, and we'd like to solve for t. So first thing we'll do is we will bring the 18 over to the other side. So 45 minus 18, that's 27. Isolating that exponential by dividing everybody by 80. So that would be 27 over 80 equals e to the natural log of 3/4 over 20 times t. And then rewrite this as per usual as a logarithm. So this would be natural log of 27 over 80 is equal to natural log of 3/4 over 20 times t. And then we can solve for t, bringing the 20 up, bringing the natural log of 3/4 down, and then we run that through our calculator and we find out how many minutes it will take. Here I ran that through and it's about 75.51, so 75.5. So my final question, or final answer to the question here, how long does it take for the cake to reach 45 degrees Celsius? It takes 75.5 minutes for the cake to cool to 45 degrees Celsius. So this one's a little bit more involved simply because there are more constants to figure out. You have K, which controls how fast you're cooling. You have A, you have T subscript S. So a lot of little work to do here, starting with your basic equation involving TS, then figuring out what A is, then figuring out what our what our cooling constant is, K, and then once we have that, we still need to address the actual question itself, which is how long does it take for the final temperature to reach 45 degrees Celsius?